What does it really mean for an AI to think? Today, we're diving deep into data structures, our strategic infrastructure. Every query, every inference, every transaction, they all depend on the underlying layout. In a world where latency budgets tighten and data volumes explode, the choice of structure gates system throughput. Modern workloads real-time recommendation, vector search, stream processing demand structures beyond CS textbooks. They are the silent architecture of performance. Choose wrong, and you trade hardware for developer pain, scaling linearly with every bottleneck. The database engine is only as fast as its data structures. But here's where it gets interesting. Mutable state is the root of contention. In-place updates force locks. Lock serialized threads, stalling concurrency. Pointer-based structures linked lists. BSTs scatter memory across the heap, evicting cache lines on every traversal. As data grows beyond a single node, distributed consistency protocols compound the cost. Traditional structures assume a sequential single-owner world that no longer exists. The result, throughput cliffs, unpredictable latency, and write amplification that kills flash endurance. These are not edge cases. They are the default in any system at scale. So what's the real problem? Let's talk about the memory hierarchy defines performance. A CPU can execute 10+ instructions in the time it takes to fetch a single cache line from main memory. Linked data structures trigger a cascade of cache misses, each stalling the pipeline. Meanwhile, dataset sizes outstrip DRAM, forcing I/O to NVMe or SSD, where latency is orders of magnitude higher. The algorithmic complexity model counting operations ignores this reality. Constant factors, not big O, now dominate. The gap between compute and data access grows wider each year. This raises a critical question: immutability, the lock-free foundation. Persistent data structures never modify in place. Every update creates a new version, sharing unchanged nodes. This eliminates locks entirely. Readers always see a consistent snapshot. Copy on write at page or node granularity keeps write overhead minimal. Functional persistence enables time travel queries, auditability, and safe concurrency. The LSM tree, a ubiquitous engine, builds on immutable sorted runs. Immutability also simplifies replication, crash recovery, and incremental backup. It turns shared state concurrency into a solved problem. Immutability is not new. Hardware trends now demand it. Now let's zoom in on cache-conscious design, minimizing stalls. Modern structures are sized to CPU cache lines. B-tree nodes fit L2, 256 bytes, reducing DRAM fetches. Skip lists use fat nodes holding multiple entries per tower. Columnar layouts enable SIMD accelerated scans. Succinct structures pack data densely to maximize bandwidth. The goal: move from pointer chasing to sequential scans. Even ON scans beat O-log N chases when cache misses dominate. Designing for the memory wall, not the whiteboard. The constant factor is the new complexity. Here's something most people overlook: the data structure stack. Applications consume abstract data types: map, set, queue, graph. Below, a collection engine selects the optimal structure family based on workload. The engine manages memory, concurrency, and persistence. Beneath, a buffer pool caches pages across I/O boundaries. At the bottom, hardware, NVMe drives, persistent memory, or GPU VRAM. This layered separation allows each level to innovate independently. Tuning happens at the interface, not in the application logic. It's the OSI model for data-intensive systems. Developers choose semantics. The stack chooses physical realization. Think about this for a second. Structure families and their niches. Ordered B epsilon, write optimized. Cache-friendly trie, mass tree, high concurrency. unordered, Swiss table, SMD hashing, hopscotch, cache line buckets. Graph CSR, static traversal, PCSR, dynamic updates, streaming edge lists for real time. Probabilistic, cuckoo filter, delayed support, count min sketch, frequency. Time series, BTRDB, nanosecond precision. Each family exploits a specific hardware property. No universal winner. Selection depends on access pattern, concurrency, and persistence model. This taxonomy organizes the design space. The right choice reduces hardware cost and operational burden. And this is where things get complex. Right path, ingestion to durability. Client write appends to in-memory log whale for crash safety. Data accumulates in a mutable, typically a lock-free skip list or hash table. When mutable reaches threshold, it is frozen and flushed as an immutable SSable file. Background compaction merges SS tables, discarding overwrites and deletes. Each SS table has a Bloom filter and index block for fast lookups. This design turns random writes into sequential I/O, maximizing throughput. Crash recovery replays the log, no data loss. But here's where it gets interesting. Read path, snapshot consistent queries. Query checks the mutable for recent updates. Then probes Bloom filters of each SS table to skip irrelevant files. For matching SS tables, binary searches the index block to locate the data block. Reads the data block, potentially across multiple versions. Snapshot isolation is free. Each query sees the state at a logical timestamp. Read amplification is controlled by compaction strategy and Bloom filter sizing. Cache misses are confined to hot sets via block cache. So what's the real problem? Let's talk about impact, throughput, latency, efficiency. Systems built on immutable cache-conscious structures deliver 10x higher write throughput by avoiding in-place updates and lock contention. Read latency variance reduced from seconds to microsecond under mixed workloads. Write amplification cut 5x through leveled compaction, extending SSD life. A major payments platform replaced 12 Redis instances with a single RocksDB deployment, halving infrastructure cost, developer simplicity, no manual sharding, no cache invalidation. These gains compound as data scale and concurrency increase. Performance becomes predictable, not probabilistic. This raises a critical question: adoption from embedded to hyperscale. RocksDB powers MySQL, CockroachDB, Kafka Streams. LMDB, a read-optimized B tree, runs inside OpenLDAP. SLED brings modern lock-free design to Rust. FoundationDB uses a custom-ordered structure for deterministic simulation. WiredTiger, MongoDB's engine, combines B-tree and LSSM. These are not niche. They underpin the infrastructure serving billions of requests. The common thread: separation of logical interface from physical layout. Standardizing on these patterns reduces operational complexity and speeds development. From edge IoT to hyperscale cloud, the immutable cache-conscious data structure is the new default. Choose wisely, and infrastructure becomes a competitive advantage. Now, let's zoom in on frontier: self-designing structures. Learned indexes replace B-trees with neural networks that predict record positions, cutting index size 100x. Reinforcement learning tunes compaction policies, Bloom filter bits, and cache sizes in real time. Near-memory processing in CXL or SmartNICs moves compute to data, reshaping structured design. The line between database, storage engine, and application logic dissolves. Structures adapt to workload without human intervention. Data structures are becoming software-defined accelerators. The future is not faster hardware, but smarter data organization. Data structures will auto-tune, auto-scale, and auto-heal.